Good morning, we are students from Group 2E for this integrated project, and these are my group mates. So there will be 3 parts in this video. For separation process, it will be mainly on the removal of contaminants in raw natural gas, and we will be focusing on membrane separation process. For reaction engineering, we will be applying the knowledge learned in this course, and the process involved is production of hydrogen via steam methane reforming process. For process modeling and simulation, the simulation of the steam methane reforming process will be done using SPIC software.
For separation process 2 part, the objectives are to draw an overall block diagram for the separation system, to design the membrane to be used in the separation unit, and also to draw schematic diagrams to show the membrane and membrane module with dimensions. Other than that, we will also need to determine the components' permeabilities and calculate the flux and selectivity.
So now we proceed with the design of the block diagram. First, we will be converting the table 1 content to mole percentage. For table 2, we will calculate the range of molar concentration of water and hydrogen sulfide in the outlet. So here's the calculation for the range of molar concentration of water and hydrogen sulfide in the outlet. For water and hydrogen sulfide, we are removing them via absorption process. For step 3, we will be removing the carbon dioxide from the gas stream via membrane separation with complete mixing model. Operating pressure is being adjusted from 71 bar to 25 bar. Operating temperature is also being adjusted from 70 degrees Celsius to 30 degrees Celsius to achieve the operating condition of the membrane. Here we will also be calculating the mole fraction of carbon dioxide in the permeate using the formula. Next, we will also be calculating the volumetric flow rate at standard temperature pressure (STP) condition of the retentate and permeate using the material balance formula. We will also be converting the STP volumetric flow rate to molar flow rate. The molar flow rate of the outlet will then be converted to volumetric flow rate. The volumetric will then be inserted into the molar concentration of water and hydrogen sulfide in table 2 to calculate the maximum and minimum number of mole of contaminants within the outlet stream. So for now, our contaminants is dropping within the range of required range. Next, we have also found the area of membrane and the flux using the formula learned.
In our design, we have decided to use PBEX 1657 as the membrane material because it has high CO2 permeability, which is 1330 barrel, and also has high selectivity, which is 45. We have also decided to use spiral wound membrane, and this diagram clearly shows the configuration of the membrane. The first layer of the membrane is the feed spacer, which allows the feed to flow through, and then we will have 2 membrane sheets, and in between the membrane sheets there will be a permeate spacer where the permeate will flow through. Next, this diagram shows that the membrane module with dimensions, and after calculation using this equation, we can find that the diameter of the membrane element is 0.4188 meter. And finally, the membrane element will be placed inside a metal shell in order to perform the separation process.
Integrated project and problem-based learning are common methods for undergraduate reaction engineering course in chemical engineering. There are a couple of objectives for the reaction engineering. First one is to design a catalytic reactor system and its sizing in order to make it as the main reactant in stage 2. Secondly, to write a reactor used for the reaction. Thirdly, to write the catalyst used complete with its properties and pricing. Last but not least, to show strategy to maximize selectivity and yield of product and maximize the side reaction. Finally, to show economic evaluation and economic feasibility of the process and the cost estimate.
Okay, now I will be presenting my part on the reaction engineering part. Firstly, for the process flow diagram, we use a mixer and a PBR packet bed reactor for our reactor system. We take our inlet CH4 from separation process, added with our water to go into the mixer. Okay, next. Next is the operating condition of the PBR. Okay, firstly, the temperature we set it to 815 to 925 Celsius with a pressure of 14 to 40 bar. The total length of the reactor is 200 meter and the inner diameter of the reactor is 0.2846 meter. The conversion rate of CH4 is 72%. Okay, next. Based on our calculation on the report, our volume of reactor calculated is 2,544.235 meter cube, and the weight of catalyst used is about 5,687.638 kilogram. Okay, next is based on that, our pricing for the nickel alumina catalyst is around 100,000 ringgit, and for our PBR reactor is about 400,000 ringgit. For the mixing tank, the price is about 50,000 ringgit. So the total of ringgit we use is 550,000 ringgit.
Process modeling and simulation is the model post representation of chemical, physical, biological, and technical process and unit operation in software. It's essentially an optimization problem which must be solved in a process. There are a couple of objectives related to this subject. The first one is to develop dynamic mathematical model for the reactor. Secondly, to stimulate the steady-state reaction process using process simulation software. Thirdly, to validate the simulation by comparing with the manual calculation. Finally, to analyze and discuss the effect of the pressure, temperature, and the feed flow rate of the reactor performance.
Hi, and my name is Muhammad Amir bin Azmi, and I will proceed for the process modeling system. So, first of all, mathematical modeling. So, for mathematical modeling, we will use the rate law for R equal to K1 over den square, PD power 2.5, multiply bracket PA PB minus PC PD cube over K1. And this rate law will be used in all component A, B, C, and D. And the mass balance is as shown below. We have one inlet and one outlet. Moving on to the next slide, which is Aspen HYSYS simulation software. So for this reaction, it will be simulated by using Aspen HYSYS. It is a well-known simulation software that used by engineers. So the fluid package for this reaction is Peng-Robinson, as we have hydrocarbon, which is CH4, methane, and the parameters for the calculation will be used from the reaction engineering part. The examples of the parameter is like inlet flow rate, inlet pressure, temperature, and also the frequency factors. And last but not least is the process flow diagram is as shown in the slide. So moving on to the how we validate the simulation. So it is used by comparing the theoretical value and experimental value. The deviation error formula is theoretical value minus experimental value over theoretical value multiplied 100%. And the deviation error is 87.86%. Before that, theoretical value is the manual calculation from reaction engineering part. Experimental value is the value that we got from the simulation software. And lastly is the effect of pressure, temperature, and feed flow rate. For this, we use the Aspen HYSYS case studies function to observe the effect of the pressure, temperature, and feed flow rate. So for the pressure, as the pressure increase, the product of hydrogen is constant. And for the temperature, as the temperature increase, the product of hydrogen also increases. And lastly, if the molar flow rate of the methane increase, so the product will be decreased. And lastly, we come to the conclusion. So we can know that the design of the block diagram, membrane material, and the membrane model, membrane separation. And for the reaction engineering part, we know that we use PBR and catalyst as our catalyst used is nickel alumina. And lastly, the simulation is done by using Aspen HYSYS software. And that's all from us. Thank you.